is to understand, what makes up the internet. So we're going to take this helicopter view, 30,000 feet view of how networks are built. We're going to understand different kinds of networks, cloud networks, enterprise networks, and broadband networks, what you are using at home. Um, Maybe you're having a DSL connection, or you might be having a fiber connection, or you might be having a cable connection at home, or you might have wireless connection, 3G, LTE, 5G, what you have. So we are going to see the different kinds of networks. And then transit and peering really deals with how networks are connected with each other. How big is actually the internet? And then we are going to take a look at the networking ecosystem. So who are the hardware manufacturers? Who are manufacturing the software? Who are manufacturing um, these optical gears? And who are the key system integrators and service providers and so on? And then the most interesting thing is to play around with packets, right? You want to see how long does it take for me to send packets to the US? What is the round trip time? What is the delay? And how do I analyze the trace route ping and so on and so forth? So how many networks are there in between and so on? So this is more the life of a packet in internet is more kind of a hands-on, some kind of experiments that we will be doing from our PC, sending packets and measuring some internet performance and stuff like that. So if somebody asks you or asks me, what is an internet, right? So what is internet? The internet is nothing but an interconnection of several autonomous systems. Okay. Um, and AS here, what's written here, AS stands for autonomous system. Autonomous system. So each box that you see here, this picture, for example, this is a box, this is a box. Each box is an individual network. So this could be, for example, Anika is a user, right? Maybe she's having a DSL connection um, to a domestic internet service provider. For example, if this is Germany, let's say this domestic ISP could be Deutsche Telekom, for example, right? She might be paying like 40 euros a month, and then she's getting, I'm just in 100 megabits per second connection. She's getting from her domestic ISP. And this box that is shown here is a complete network. And Deutsche Telekom is building this network and managing this network. So Deutsche Telekom will put many routers in to build this network because Deutsche Telekom is the main internet service provider in Germany. And Germany is a big country, and have so many cities. So Deutsche Telekom might have, like, I'm just throwing some numbers, right? They might probably have 10,000 routers inside Germany interconnecting all the cities and so on. So this is a very high level view. I'm abstracting all those details. So this whole box that is shown here is a network that Deutsche Telekom is building, and it is represented, each network has an autonomous system number. The 65000 is the autonomous system number, and each network has to have this unique autonomous system number. Okay. And Deutsche Telekom is a regional player, right? He's there only in Germany, probably in East Europe, and a little bit in the US, but he's definitely not there in Australia. For example, this customer, Rui Jiao, probably she's having an LTE wireless connection to her domestic ISP. In Australia, there is an ISP called Telstra. They are a big internet service provider in Australia. And the customer in Australia, Rui Jiao, she's connected to another autonomous system, and this autonomous system or this network is built by Telstra, who is the national player there. Now the question is, how can Deutsche Telekom um, communicate with Telstra, who is in a different continent, right? And you need to interconnect all these networks together. And then comes some special kind of networks called global ISPs and transit providers. These global ISPs and transit providers, they don't have any direct customers, like they don't sell any DSL products like what Deutsche Telekom or Telstra would sell. But global ISPs and transit providers are kind of interconnecting networks. They connect several domestic ISPs with each other. So if Anika wants to exchange a file to Rui Jiao, she will send her packets first to the domestic ISP, right? In this case, it's Deutsche Telekom. And Deutsche Telekom will then send the packets to the global ISP, and the global ISP will send it to a transit ISP or the transit provider, and the transit provider will send the packet to the local to the domestic ISP in Australia, and the domestic ISP will, through the LTE connection, you are sending the file. So that's how the communication happens. So in a broader sense, internet is nothing but a connection of several networks, and each network is managed by a different company or a different kind of an organization. For example, as I told you, the domestic ISP in Germany could be Deutsche Telekom. A global ISP is a completely different company. There are many companies in this space, but to give you one example, GTT, there's a company called GTT. They have networks throughout the world and they're connecting. That's why they're called a global internet service provider. And transit providers, for example, level 3, there is a company called L3. I'm going to give you the names of all these players, right? So these, the unique thing about here is that each network, right, is built by a completely different organization, and each organization will have their unique autonomous system number. For example, you see here in all these pictures, each of these boxes, they have a different autonomous system number. Deutsche Telekom has 65000, and GTT is having 65010, and level 3 has 65501, and so on and so forth. If you want to build a network in internet, then you need to have an autonomous system. You need to get this autonomous system number first, right? We'll talk about autonomous system numbers, where you can get this autonomous system and so on. And so far we have seen three kinds of networks. One is the domestic ISP. Domestic ISP will usually sell you products like DSL or fiber or cable and LTE, 3G, and so on, right? So the end users like Anika, like you and me, for example, I'm now connected to an ISP called Vodafone through a cable network. So I am someone like Anika getting broadband connection from my ISP. So this is a domestic ISP. And then there are some special networks like cloud providers, like you see it here. Some examples of cloud providers are Amazon. You might have heard about things like AWS, Amazon Web Services, right? Or Microsoft Azure. These are cloud providers. Or Google. For example, if you are watching any videos in YouTube, right? Mostly it's coming from Google Cloud, right? It's a network managed by Google, right? So if you are watching, for example, Anika is going to watch a YouTube video, then she is going to probably get the content from the cloud provider. And the cloud provider, how is he connected to the internet? He will have his router right here connected to the transit provider. Once you connect to a transit provider, um, you know, then you can be sure that the transit provider is going to give you access to the rest of the network. So the transit and the global ISPs are the kind of the backbone guys who are tying the whole internet together. And the domestic ISPs and these cloud providers are, guys who are having the content. For example, Netflix, right? Netflix is also streaming stuff from the cloud. So all these kind of content providers, Facebook, Instagram, and so on, all these services are there in some kind of a cloud, right? And how do you connect to the cloud? through the transit on the global ISPs. And then you have content providers. It could be Netflix or other video streaming services, right? So they have their own autonomous system and they have their own network. They might be connected to the transit providers. And then enterprises, as I told you, banks, right? Or insurance companies or travel agencies, big travel companies, and any enterprises like furniture shops like IKEA. They might have branches in many countries. So each enterprise will have their own network and they need to be connected to the internet. Either they can get connected to a domestic ISP or an enterprise can also get connected to a transit provider. And once you establish a connection to either a domestic ISP or a transit provider, then it means that your network is connected to the internet. Then many people around the world, right? A domestic ISP in South America, then they might be able to send packets to you or access some servers inside your network and so on and so forth. So the key takeaway from this message, from this slide, is that the whole internet is nothing but a collection of networks, and then each network has a unique autonomous system number. A network is a representation, right? I mean, Deutsche Telekom is just the name of the company. But from a networking perspective, each network should have a unique autonomous system. So I'll be using this word again and again, autonomous system. You just need to be aware of what an autonomous system is. An autonomous system is nothing but it represents a whole network built by a company, and an autonomous system, it could be very small. You can build it with just 2 routers, or it can be as big as Deutsche Telekom, who could probably build their network with 10,000 routers, or IBM Cloud, where I work, we have around 50,000 routers around the world, and so on and so forth. So networks, each network can be of different size and complexity and so on. We'll talk about it later. But at least from the interconnection perspective, from a broader perspective, the whole internet is nothing but a connection of several networks of different size, each with a unique autonomous system. Okay. Is there any questions so far in understanding this? You can put your questions in the chat, or you can, um, just speak out in the channel. Okay. I assume that this is clear for you. And another thing that I have shown in this picture is that I'll put some routers here. Right, each network, what they will do is they will put a router at the edge of their network where they are bordering another network. And these routers are called as edge routers, and they'll be running the protocol called BGP. BGP stands for Border Gateway Protocol. We'll be talking about this. So this protocol BGP is kind of the only standard protocol through which networks talk to each other. Okay, we'll talk about that later, but just have this in mind. You don't need to know what a BGP is at this point, but an internet is nothing but a connection of networks, right? It's an interconnection of networks, and you use BGP as the protocol. So ISP stands for Internet Service Provider. That was a question. What is an ISP? ISP stands for Internet Service Provider. What is the difference between the two types of routers? Okay. This picture I have shown is a Juniper. So this picture is the Juniper router, and this is a router manufactured by Cisco. It's just shown in this picture, but they are just routers manufactured by different companies, right? But we'll talk about all those stuff later. Okay, don't have to worry about that. This picture just tells you that you can build your network using your own equipment. You can use routers from different router manufacturers. Okay. So let's go to the concept of autonomous system. An internet is a collection of autonomous system. And as I told you, each autonomous system is a network built and operated by an organization. It could be Deutsche Telekom. It could be, an AWS, Amazon, Facebook will have its own autonomous system. And as I told you, each autonomous system has a unique autonomous system number. And it's a kind of a hierarchy, right? If you want to start your own network, what you need to do is first you need to get an autonomous system number, right? First you need an ASN number. Excuse me. Oh, I'm having some difficulty with this. So I'm going to just introduce you to one node that I usually use for my drawings here. So let's assume that you want to start your own network, right? So what you need to do is you need your own autonomous system. You need to first register to, let's assume that you are in Germany, right? And in Germany, there's an organization called RIPE. And this organization is going to give you an autonomous system number that will be very unique, okay? And once you get an autonomous system, the next thing that you need is some IP addresses. So you can either get some IPv4 address or v6 address. And who's going to give the IP addresses? Again, RIPE, right? So RIPE is an organization who is managing the IP address allocations. So once you have an autonomous system and once you receive some public IP addresses, in IP addresses, there are two categories. You have public IP addresses and you have some private IP addresses. We'll talk about that later. Private IP addresses you can use only inside your network, right? So you cannot, it's not routable in the internet. All these IP addresses, you cannot route it in the internet. Whereas the public IP addresses, you can use it globally. So you need those kind of public IP addresses if you want to connect to the internet, right? So you can get the public IP addresses from RIPE. Either you can get v4 addresses or IPv6 addresses. Once you have a valid autonomous system and an IP address associated, then you build your network. So this is your, let's say this is your network. I'll call it as, let's give it a name. Let's say you're building the network X, right? So you put a couple of routers, right? And once you have, so your network, you're starting off very small. You just have a couple of routers and you have an autonomous system number, right? So this network has an autonomous system number. Let's say you got an autonomous system number 100, right? And then now it's time to interconnect your network to the internet. So what you do is you talk to an global ISP, right? Global internet service provider, and then global internet service provider will have his own router, and a global ISP might have several routers in his network, right? And then you put a cable connecting your router to his router. It could be a 10 gig link or it could be 100 gig link, depending on how much of traffic you're going to exchange, right? And then once you connect your network to your global internet service provider's network, um, then you need to configure some routing protocol. As I told you, you will be configuring a protocol called eBGP between these two routers. Let's call this router 1 and router 2. You'll be configuring eBGP between these two routers, and then your job is done. The global ISP is connected to the rest of the internet, right? So the global ISP is there everywhere. And so you don't need to worry about connecting, whether your network is now connected to the rest of the world. So you have made a contract with the global ISP. The global ISP is going to give you internet access to the whole internet, right? So once this basic step is done, once you have your autonomous system, once you have your public IP address, and once you connect your router to your global ISP, and then I'll talk what else you need to do. But once this connection and this BGP is there, and once you advertise your IP addresses to him, then you're pretty much sure that you're reachable from rest of the world. For example, someone in Australia, right? Some network in Australia, someone who's connected here might then be able to somehow come via global ISP and then will be able to reach you. So this is the kind of stuff that happens in the broader internet. This is what you will essentially do when you build your own network. Okay, so I already see some questions. What is layer 3, level 3, and how these big players are connected? Do they pay each other? Okay, I'm going to talk about all these things in this class. Can you use public IPs in a local network? Yes, you can use public IPs in a local network, but you'll be wasting the public IPs. You don't want to use them because they are getting more expensive now. And what is the difference between V4 and IPv4 and IPv6? We will have a big discussion about that, so just hold on for now. Yeah, we will deal with all these questions later. But we are now discussing about a much bigger picture, how networks are connecting with each other. Okay. So we learned that you need you need an autonomous system number, and you need some public IP addresses so that networks can connect to you. For example, Google has an autonomous system number of 15169. Deutsche Telekom has an autonomous system of 34086. And as I told you, each company, right? It's not only that you get an autonomous system, right? You need autonomous system, and you also need IP address. You need to buy IP address that belongs to you, and the IP address that RIPE is going to give you, it's only for you. That means every autonomous system is bound to certain IP addresses, right? So it's your identity, right? Like how a name uniquely identifies you, or how an email address uniquely identifies you. An autonomous system number and the public IP addresses that are allocated for that autonomous system by RIPE or whoever is going to assign it, they uniquely identify the network. That means like Google has an autonomous, unique autonomous system, right? Google has an unique autonomous system 15169, and this number will not be assigned to any other network or ISP. Okay, and Deutsche Telekom has 34086, and no one else get this number. It's very unique for Deutsche Telekom, and Deutsche Telekom will also get its unique IP addresses. We'll talk about all these stuff and how do I find out which IP addresses Google is owning, and all these stuff I'm going to show you in today's class. Okay. And once this is clear, there are different kinds of autonomous systems, right? Uh, we saw about different categories of network providers. One category is domestic ISPs, like in Germany you have Vodafone, Versatel, Deutsche Glasfaser, who's giving you FTTH or fiber connections. Net Cologne, you will see in Northern Westphalia, Unity Media, Deutsche Telekom, right? So all these are domestic ISPs. They are selling you broadband connections to you, or LTE, 3G LTE connections. And then you have these transit providers, right, or the global ISPs, who are kind of present in all the continents. And for example, how will you connect your network to some network in US, right? So all the transit providers come into this game now, level 3 entity. Deutsche Telekom is also kind of a transit provider because they are quite big. And then you have the cloud providers like Google cloud, Microsoft Azure, IBM Cloud, AWS. By far, AWS is the biggest cloud provider in the world, having around 50% or even 60% market share. And if you are watching Netflix videos, right? Netflix is hosted in Amazon. So whenever you are watching a Netflix video, most likely you're connecting to an Amazon cloud or AWS cloud. We'll talk about, we will see that how it works, right? And then you have the content providers like Google, Facebook, Spotify, Netflix, and so on. They build their own networks, and um, yeah, Google by far, the kind of network they have, with the kind of services they are dealing. If Google's network was a separate network, they will be the biggest network in the world and the most complex network in the world. And Google has been in this industry for building these kind of stuff from, I don't know, like 2004, 2005. That's the time frame that they came in, right? So, but all these guys like transit providers, and these guys are there from the time when internet started, 1980, late 80s. So, they are there pretty longer. But all these content providers, right? They are pretty new players into this space, but they are much bigger. They have grown much bigger now, because most of the people, what they are doing these days, they are either in Facebook, Instagram, or Google, and stuff like that. So the content providers, their networks has become very complex in terms of how they build a network, and also in terms of how much of volume of traffic that that comes to these content providers. So this becomes very interesting. Also this cloud and content is where most of the fun activities happen these days. And these domestic ISPs are giving you access to the internet, right? So this is a totally different ball game here, right? So these are called as the eyeball networks. You'll also hear this term eyeballs. Eyeballs means people, right? So guys like you and me who are getting connection from home, broadband connections, right? And what are these eyeballs doing? They are getting content from the content provider or the cloud provider. So the eyeballs are now talking to the content providers, getting the content. And most of the content is mostly download, right? So you're watching movies, there is a lot of traffic coming from the content provider towards the domestic ISPs and so on. So this kind of internet traffic patterns also is very asymmetric. The amount of traffic going out of the domestic ISP is less, but the traffic coming inside a domestic ISP will be more, because predominantly a lot of people are watching videos these days, and video is mainly a kind of a download or downstream rich content, right? So all these factors come into play. So in this slide, it just explains the different kind of autonomous systems out there. And who manages the autonomous systems and IP address? There's an agency called IANA, which is a global internet agency, what we call as the Internet Registry System. And they have regional, continental offices. For example, in America, it's called ARIN, and in Europe, it's called RIPE. And in Asia Pacific, it's called APNIC. In Africa, it's called AFRINIC and LACNIC. So if you are going to build a network in Africa, for example, then you have to contact AFRINIC, and AFRINIC is going to give you, AFRINIC is going to give you the autonomous system numbers and the IP addresses that you need so that you can connect your network to the rest of the internet. And we are in Europe now, and in Europe, if you want to build a network in Germany, um, you need to contact RIPE. RIPE is going to give you the autonomous system, right? So these are the regional internet registries called the RARs, because they are spread across the different regions in the world. And there are some historical significance, right? I'll talk about that later. And then what happens is this IANA is this global organization, and if you are in Europe, living in Europe, then RIPE is the agency, and all the big telecommunication companies are coming under RIPE. Like Deutsche Telekom is a kind of a LIR. LIR is called as the local internet registry. So RAR is the regional, and the LIR is the local internet registry. And if you start a company and if you're building a network, you have two options. Either you can, get your autonomous system number and IP address from the LIR, or you can directly contact RIPE, and RIPE can give you IP address and autonomous system number. So there are two different options you have. But it doesn't matter. You just need to, know that there is a certain kind of structure here, the global organization, a regional organization, and a local organization. And those are the organizations who are giving you the autonomous system numbers and the IP address that you need to build your network. So the internet, there's a hierarchy here. So for example, let's take a case like this. So Anika is a user, right? And she has a contract with a domestic ISP in Germany. Let's say it's the 1&1 Versatel, 1&1 Versatel. And 1&1 Versatel has a unique autonomous system number, 8881, which has been assigned by RIPE. Okay. And Anika is getting an IPv4 address like 46.142.0.10. It is one IP address. Okay. And who is giving the IP address, this public IP address to Anika? It is the domestic ISP. Versatel is giving this IP address to Anika. So how do they give? Anika is probably having a DSL connection. And as soon as she switches on her DSL router in her house, she gets connected to the 1&1 network, the domestic ISP, and they are going to assign her an IP address. And once you have this IP address, if you look at the domestic ISP as such, they are having a bigger block. They are having a block called 46.142.0.0/16, okay, which is a slightly bigger block. So what is this concept of bigger block? So we are going a little bit into IP addressing now, right? So what is this concept of bigger block? So let's say you are the home user, right? So you are having a DSL connection at home. So this is your DSL router at home. And then you are connecting your DSL router to some router from your ISP, right? This is your internet service provider, right? So your internet service provider has an autonomous system number like 8881, and then he has an bigger block. He has an IP block that he received from RIPE. So he's gave, let's assume the IP address that the RIPE has given to this IP, to this ISP is 8.8.8.0/24. I'll talk about this. So this is what we call as a subnet. Okay, it's a group of IP address. So the /24 tells you how many IP addresses are there inside this subnet. So inside the subnet, there are roughly around 200 IPs. Okay, so from these 200 IPs, your ISP is going to give you just one single IP. So for example, the IP that your ISP might give you is 8.8.8. Let's say 5. Okay, this is a single IP. But this single IP belongs to a subnet or a bigger block. And this bigger block is called as the aggregate. So it's something like the IP addresses are organized as a kind of an tree. You have an aggregate, right, which is something big, right? It has several IPs. assigned by, RIPE or any agency. And from this aggregate, you can split the aggregate into many smaller IPs, and you can assign these smaller IPs to your customers. So in this case, when you are, because you're a DSL customer, you don't need more than one public IP. But if your ISP is also um, servicing a bank, for example, right? Maybe the bank needs more IPs. Maybe the bank needs 5 public IP addresses. You can give that, no problem. Maybe the bank is getting 8.8.8.6, 8.8.8.7.8.9, and .10, and so on. So the bank is getting 5 IP addresses. But you as a DSL provider, you don't need that many IPs, right? They charge you quite a lot for how many IPs you get. But the key point is your ISP is going to split the bigger block of IP that he received from RIPE, and then he's going to give individual IPs to you. And this is the fundamental concept of IP that we call as subnetting. Subnetting means you are somehow having a bigger block of IP, and from this bigger block, you can make some smaller blocks of IPs, and you can still break it down even further down, right? So this concept of breaking down a bigger block of IP address into a smaller block is what we call a subnetting. I heard that you had this in one of your earlier semesters, right? So how many of you know how to do subnetting in IP? You had it in your previous semester, right? Can you reply in chat? Okay, I see predominantly a lot of people are telling this with yes. So from an examination point of view, you will have some questions on subnetting. Okay, we will discuss some stuff during exercises. Okay, but at least from a conceptual perspective, you know why we are doing the subnetting. If you are an ISP, the RIPE is going to give you a bigger block, right? He's going to give you a bigger block, and which you have to divide into many smaller sub blocks, right? By the process, applying your subnetting skills, and then you will split into many smaller blocks, and then assign those IP addresses to your customers. Maybe this block, will be given to a bank, and you're going to assign this this block to an insurance company, and you can only assign one IP address to a DSL customer, for example. It's completely your design, but you just need to know that where is subnetting applied. If you are an ISP, then you get a subnet, you get this IP address, public IP address, a bigger block from RIPE, do your subnetting, and then distribute your IPs to your customers. Okay, does it make sense? So that's how each user in the internet gets a public IP address. Okay, let's get back to the picture here. So now it should make sense. The user Anika, right? Let me take my pen. So the user Anika, right? She's a DSL customer. She gets only one IP from her ISP. But look at the ISP. The ISP has a bigger block. A /16 represents a bigger block. But Anika, she's getting a /32. A /32 represents a single IP address, right? As /16 will have thousands of IP address. From these thousands of bigger group, Anika has been given one IP. Okay. So what else needs to be done? Once you develop your network, right? You get your ASN, you get the IP address from the RIPE and so on. You need to get connected to your global ISP, right? In this case, the global ISP is level 3. And you can see the global ISP has an autonomous system number, and he's registered to all the regional internet registries because the global ISP will be there in all the continents. He can connect to South America, North America, Europe, Africa, Asia, and so on. So he will be registered in all the RIRs that we saw before, right? And the most important thing you need to do is you have to tell the global ISP that you own this block. So the global ISP needs to know what the global block is. So this global block 46.142.0.0/16, you need to tell the global ISP that you are owning this IP address. You make this announcement through BGP protocol. So what is this? This is the key thing in internet, right? In internet, what you need to do is the IP addresses that you have has to be shared with the rest of the world. Just like, for example, if I want to make a telephone call, what do I need? I need the other person's telephone number, right? Or if I want to send a post to someone else, what do I need? I need the postal address of the recipient, right? So it means that all the networks in the world, they need to know your, I'm assuming that you are working in this company, right? For this moment, let's assume that you are working in a domestic ISP and you have just now built this network. If the whole world wants to send packets to you, then you have to announce yourself telling that, hey, I am versatile and I have this autonomous system 8881 and I have the following IP address. You have to make this announcement to your global ISP. And what the global ISP is going to do, he's going to internally announce that announcement. He's going to forward this announcement to his customers. And the transit ISP, he's going to make this announcement to the cloud provider and the domestic ISP and so on. So the domestic ISP in Australia now knows about 46.142.0.0/16. They know that there is a new network called Versatel with an autonomous system of 8881. And if I can now send packets to them, right? So this is what we call as the advertisements. So advertisement is like if you have a new product, you have to advertise, right? You have to tell the rest of the world that you have a new product, right? So in a similar way, in IP networks, we use protocols like BGP or OSPF to make these advertisements. An advertisement is nothing but you are letting know other people or other networks that you own this IP address and you own this autonomous system number, and anyone can send packets now. Okay, so that's it's a very broader idea of what an advertisement is. Is that clear? We will talk about BGP. When we talk about BGP and OSPF, we'll look exactly at how an IP is announced. But the key concept to understand is you are letting other people know that you are there in this internet, right? So that's the concept of advertisement. That's very key in understanding internet. So I want to discuss now some key IP addressing concepts. These are kind of a core set of concepts that you need to understand, right, before we move on to anything. So things like, why do we need an IP address? What are the different versions of IP address? And the hierarchy of uh, IP address, and how do you share the IP address, right? You need to share, like telling your friend, like exactly telling your friend you got a new number. For example, you make a new telephone connection, you need to share the number with your friends and family, right? So you need to share the IP address. Exactly, it works exactly the same. For example, if you move into a new apartment, right, you need to tell your family and friends that you moved into this apartment, or tell your whatever, right? So exactly this happens in the IP world. You do this with routing protocols, right? So let's compare the internet to the postal system that we all know, right? What do you do when you send a package to someone, right? The first thing you do is assemble the package, right? Put it in a kind of a brief or a box, right? That's the postal world. But internet, what you do is you call it as a packet. You put everything in a packet. You put everything in a packet, right? So that's the internet term for this. And the second thing you need to do once you put, you know what stuff you do. For example, this packet could have something like you want to watch Netflix, for example, right? So that's a packet. You want to send that to Netflix, right? Or that's a comparison to the postal system, right? And then the next thing you want to do is to put a name on the package. You need to know which person is getting the packet, right? You put the name Mr. John is the recipient of the packet, right? In the internet world, it's represented by the domain name, right? For example, if you are browsing a web, CNN.com or BBC.com, so that's the kind of domain name, right? So now the next question is, you need to know the address of Mr. John, right? So either you look in a phone book or get it from the receiver directly, right? So in the IP world, there's something called DNS or domain name system, right? So I don't know the IP address directly. I need to go through this. I'm just typing CNN.com in the website, right? I'm missing an O here. I need to fix it. CNN.com. I don't know the IP address of CNN.com. So that will be resolved by a lookup process called DNS, right? It's a protocol. We'll see that soon. What the DNS is doing is whenever I type www.cnn.com in my web browser, the browser is going to ask a DNS server, okay, what is the IP address of CNN.com? And the DNS server is going to tell you the IP address of CNN.com is 6.6.8.8. Okay, so that's the work that the DNS is doing. So once you have the address, then you put the address on the package, right? You put some address on it, right? So this address in a postal address looks like this, but in the IP world, the networking world, it looks like this, right? So this is the address. You put an IP, you put an address on the packet you have generated before. And then what you do is sometimes you send a registered mail, right? You need an acknowledgement. You want to make sure that the packet really reached the recipient. So in the IP, in the internet world, we do that with TCP. A TCP is a protocol where it runs on top of IP. It's going to tell you whether the packet reached the other end or not. It's done through acknowledgements. So it's to make sure that no packets were dropped somewhere, in the internet. There's an alternative to it called UDP, which is a best effort service. There is no acknowledgement. You just send the packet, that's it. You don't get an acknowledgement whether that packet reached the receiver or not. So if you are looking for some kind of an reliability, then you use TCP. And then finally, what you do is you ship the package, right? You go to the nearest post office and then put the box, letter or package, hand it over to the post office, and they are going to use a truck, airlines or ship, whatever they have as intermediate points, and they're going to deliver it to the destination. And in the internet world, they are going to be processed by routers, right? So there are going to be a lot of routers in between from the source to the destination, right? Before the packets reach. So this is a very good comparison of a postal system versus the internet. This is how stuffs basically work. I think this should be pretty clear from a conceptual point of view, right? So coming back to the first question, why do we need an IP address, right? An address is a unique thing in the whole internet. If you go to the previous picture, if you want to get connected to the internet, you need some unique IP address. That's your identity. If somebody wants to send you any IP packets, then IP, that somebody can be anywhere, right? He can be in Australia, or it can be in South America, or it can be in North America. And they need to send you IP packets through many networks, intermediate networks, right? And all these intermediate networks have to can only route a public IP address. If you are going to have a private IP address, and let's say you have a private IP address and you cannot nobody can send a packet to you if you own a private IP address, because the public IP addresses are unique. We'll talk about that later. But coming back to the discussion, why do you need an IP address? That's your identity in internet. Especially the public IP address is the identity. Things can be slightly different, right? For example, uh, normally at home, you don't even realize what IP address you're using, right? And your IP address will also be changing every time you reboot your DSL router, or every 2 to 3 days, your ISP is going to change your IP addresses. But internet somehow works, right? You don't really care about what IP address your ISP is giving you, right? But companies like banks and insurances, they need some fixed IP address. They don't want IP addresses to change over a period of time. So they are assigned what they call as the static IP addresses. But mostly DSL customers, when you're behind at home having a normal connection, you are going to get a dynamic address. Your ISP is going to give you dynamic address. That means the IP that you receive will be public, but it's going to change. It's not going to be the same. If you log into your router tomorrow, you're probably going to have a different IP, right? So that may be good or bad for you, depending on what you want to do with the IP address, right? So any fundamental questions on this? Is it clear? So just if you want to know what IP address you are behind, you can just go to Google, right? And then type, what is my IP, right? And then Google is immediately going to tell you this is your IP. For example, the computer on which I am connected, right? I'm getting an IPv6 address. It looks complex, right? You can't remember this, forget it. It's in hexadecimal, quite huge. But some of you might be in IPv4. I mean, all you have to do is just open your browser now and then go to Google and type, what is my IP? And it's going to tell you which public IP address um, you're having, you're currently behind, right? So there's a question in the chat, what is the difference between a global ISP and transit ISP? We'll talk about that in a while. That's a very subtle difference, but it's just put it in the picture. But you just have to think at this stage, a global ISP and transit ISPs are kind of backbone guys connecting several smaller networks or domestic ISPs with each other. Okay. So any questions so far in this comparison to the postal system? I think it should be clear. And people always talk about, something called as this TCP/IP reference model, right? So this is the TCP/IP reference model in our OSA reference model. It's just a reference model of what happens exactly inside your host machine. So this could be your Linux machine or Windows machine or Mac in which you're working. Let's say you are doing a HTTP, right? Let's say you're doing some browsing, you're opening a browser. So a browser like Chrome or any browser that you might use is actually an application, right? So the application in turn is using a protocol, an application layer protocol called HTTP. So you open Chrome and then you type you type www dot google.com, right? So this is something that you do in your application like Chrome or Internet Explorer or Firefox, any web browser, Edge or whatever you have. At the background, what this application is doing is they use a protocol called HTTP, right? So that information, this is your user data. So user data is actually www.google.com, right? And then you put in that data that is generated at the application layer. When it comes to the application layer, the HTTP is going to add an application header to it. It's an HTTP header. We will see that, right? So this is the actual user packet, right? At the application layer, an application header is added, and HTTP will run on TCP. And TCP is at the transport layer. It will add its own TCP header, It'll put things like the port numbers, the source port number and destination port number and so on. And then this complete thing is the application data, right? So now you're adding a TCP header at the TCP layer, and then the TCP layer is going to hand off the packet to the network layer. So for the network layer, he's going to add an IP header. IP header, it means you're going to add the source IP address and you're going to add the destination IP address. In our case, because this is google.com, your destination IP address is going to be an IP address of Google, right? You will add this IP, the network layer is going to add that. And then you send that packet to the data link layer, and Ethernet is the most, PPP and SLIP are very old technologies, and forget about them. Ethernet is kind of the de facto now Ethernet standard now, are the only data link layer that's predominantly like 99% you'll have only Ethernet layer. It's going to add an Ethernet header, right? It's going to put all these other things inside the Ethernet header, and then you're going to send it through the wire, right? So this will be your DSL connection. So all the stuff that you see here are happening in the host, right? So only the application, your Google Chrome, right, is running as an application layer. All the rest of the stuff here will be part of your kernel. They'll be part of your kernel, whether it could be Linux kernel or every operating system will have an kernel. And anything about the kernel is the user space, right? So these are all just running as a process. When you hit Control Alt Del, you see all the processes are in Linux. You have a command called process ps minus aux that lists you all the processes. All these are application processes, right? And then the rest of the stuff, this TCP, IP, Ethernet, all these are part of your operating system. So Mac, Linux, Windows, they all have their unique TCP stack, IP stack, and Ethernet stack. All these things are there inside your PC, right? So this is how packets are sent out from your computer, from your laptop, or this stack is also present in your mobile phones, right? So whether you're using Android or any mobile, you're going to have this entire stack, TCP, IP. So this is going to be pretty much the same, right? So all your apps are the ones that you use, all the applications, right? It could be a browser or it could be any app. But at the background, you need some kind of um, all the applications will do a kind of a socket programming. Has anyone done socket programming here? Yeah, someone's, some CPU, you can write any C++ program, you can write your own, C++ code or Python code or any code in user space. And then every operating system will have a socket API through which you can access TCP or UDP, and you can uh, really start developing those stuff. But behind inside the kernel, you have TCP and IP and all these routing stacks. And this is what exactly happens when you send a packet out to the internet from your machine. So I already see some questions in the chat. I will answer these, and then we'll take a short break. Um, so the question on global versus transit, we'll answer it later. Who has static ISP and who has dynamic? So mostly all DSL customers, like you and me, are behind a broadband connection at home, you'll be getting dynamic. And if you pay more money to your ISP, he's going to give you a static ISP. It's a little bit expensive. Like banks, small, medium businesses, they don't want to change their IP addresses because they might have some public servers behind. If you change your IP address frequently, then that's not good. So those kind of people, they can get static IP. How many border routers does an autonomous system need? So it really depends on how big your network is, and we'll talk about that soon, right? So that really depends on how big your country is, your geographical spread is, right? For example, Deutsche Telekom, right? Let's say if he's operating in Germany, he has to put these kind of border routers in some key cities like Frankfurt, Stuttgart, Munich, Hamburg, Düsseldorf, Berlin, and stuff like that. So that's kind of really depends on how big your country is, and there are other factors to that as well. So what's the advantage of dynamic IP? There's no advantage. I mean, it's just an IP address. It's just there is nothing. But just looking at an IP address, you cannot say whether it's static or dynamic. It's just a dynamic IP is assigned to you for a certain time frame. It could be 1 day or 2 day, and after that, you're going to get a different IP. That's it. A static IP address will remain with you for 1 year, 2 years, depending on what kind of contract you have done with your ISP. Um, one advantage maybe a dynamic IP is, you know, probably you might get some less attacks, right? If I know your static IP, then I can do some DDoS attack, right? I can send too many packets to you and things like that. But if my IP address is dynamic, probably I'm getting a little bit of security from that perspective. But from a routing perspective and stuff like that, there's no real advantage. So there's a question on the channel. I mean, the question was, why do we need to subnet when we all can share the IP? Let me explain you why we need to subnet. So when we are building a network, right? The internet, your network is kind of built as some kind of a hierarchy, right? So what you'll do is you will have one main router, right? So let's call this as the edge router. The edge router will be connecting to other ISPs, right? So this is where you have your eBGP connection to other internet service providers, okay? And the edge routers, you might be serving different geographic locations, right? So let's say you have 3 sites in 3 different cities, okay? And this particular router will be connected to 3 different cities. Let's say you are a very small internet service provider, uh, providing internet to Cleveland, uh, Fort. I don't know, I'm just writing some city names, right? Duisburg. So let's say you are offering internet services here. So what you normally do is you put separate routers in each of these 3 cities, right? And then interconnect it to your edge router. And then all your customers will be connected here. So these are your customer connections in each city. So here are all your customers, right? Right. So the bigger block that you got was like 8.8.8.0/24, which has roughly 200 IPs in it. You know, but you have 3 different sites, right? Clever and Cumberland Ford and Duisburg. So generally in IP, what you can do is you can divide the /24 into 2/25s. When you divide the /24, then the subnet mask will get a /25. That means you're roughly dividing the 200 like into 200s. Okay, and then you can go a little bit deeper and divide this block into its component /26. Then this 100 will roughly split as uh, sorry, I need to think I made a mistake here. So you divide the /25 into 2/26, each with 50 addresses. And similarly, you can do this as well. Divide this /25 into /26, and each having roughly 50 IPs and so on. And what you essentially do is you assign certain ranges, right? So this one, you give it to Claver. And this range, you give it to Duisburg. And this range, this /26, you are giving it to Cumberland Ford. And this could be another city. And if any customer is connected to Cumberland Ford, right, they are going to get an IP from this block, from this /26. Of course, this /26 is part of a bigger /25, and everything belongs to the parent /24 block that the RIPE gave. But this is the whole concept of subnetting. That's what service providers do, because the whole network will be split into different cities. For example, if you are, a big ISP, or if you are an enterprise, right, you will have different departments like marketing. You'll have a department for HR. You'll have a department for sales and so on. And each department will have its own router, and they will have their own IP prefix. I mean, an IP range. But the edge router, when it is talking to the other ISPs, he's only going to tell that 8.8.0/24. The bigger block will be announced. This announcement that I was talking about, only the bigger block, what we call as the aggregate, right? That will be announced to the other ISPs like Transit or global ISPs. Because the global ISPs and other guys, they don't need to know actually how internally we have organized our things. All that the global ISP is going to do is he send the packets to him, send the packets to our edge router. The edge router needs to know where is that particular customer. Is he in Duisburg, or is he in Cumberland Ford, and so on. So edge router is really the router that needs to make a decision as to where the packet has to be sent. So they need to know about all these, what we call as the more specific prefixes. So when you're doing a subnetting like this big prefix is called as the aggregate. And as you go down, you split and split and split, and then you make several smaller subnets. And these subnets are called as the more specific prefixes. And these more specific prefixes are not interested for the global internet. You should not announce these more specific prefixes outside your network, because for a transit provider, you are a complete network. You are seen as an aggregate. Any packet that belongs to this aggregate, he's going to send you. But only at the edge, you really have to make a differentiation whether the packet needs to go to Claver or Cumberland Ford or Duisburg, right? So the more specific prefixes will remain within an autonomous system, right? That's something internally, that's something an internal design that you should never share it with your transit or global guys. Did that answer your question, Ahmed? Cool. So this is my, the hand scribblings that I'm drawing. You're also going to get this, right? I'm going to save them as a PDF file, and I'm going to upload it in Moodle under the section whiteboard notes or something. So at the end of the lecture, I will do that. Just to know that, you haven't, maybe it makes sense to you when you go through this at a later point. Great. So next, coming back to the network architecture, we saw this, what happens inside the host, right? The TCP IP reference model. We went through that. And then let's take this chance to actually look at some, how exactly an IP packet looks like. We'll take a look at an IPv4 and an IPv6 packet. So I have already installed the software called Wireshark. But let me explain you what Wireshark is doing. What Wireshark is doing is like, if this is your laptop or PC or mobile phone, whatever, let's call it as host, okay? Each host has something what we call as the kernel, whether it's Windows or whatever, yeah? And then we have something called as your network interface card. NIC is your network interface card, right? Where you can physically connect a wire to your DSL router or your home router, right? Either you do it physically using an Ethernet wire, or you also have wireless NIC cards, right? So you're connected mostly by wireless LAN, right? So this is a wireless NIC card, but from a kernel's perspective, everything is a NIC, network interface card, right? And what we are doing is we are installing a software called Wireshark. And what this software is doing is it basically sniffs all the packets coming in and out of all the network cards. Let's say your packet is coming in from your DSL router, it's going in, and some packets will come out from your PC going out, right? So it's going to sniff all the packets from your NIC cards, and then it's going to display you in a GUI, graphical user interface. That's basically what a Wireshark does. And for that, you need to when you're installing that, Wireshark is going to ask you, shall I install a tool called PCAP? You need to give permission. That means you're allowing Wireshark to actually sniff packets coming into and leaving on the network. One important tip that I want to give you is after installing, if you're not seeing any packets, check your maybe you've installed some firewalls, some antivirus stuff like Norton. I don't know. There are so many softwares. They might think that Wireshark is kind of not secure, and they might block you from sniffing those packets. So I have seen issues where people they could not sniff these packets because their firewall or some rules in their PC was stopping them. So you just need to disable the firewall, and then you should be able to sniff all those packets coming in and going out of your PC. Okay, so I'm going to have a separate session on how to sniff packets with Wireshark and so on. But in this class, I'm just going to show you how a IP packet looks like, right? I just want to, in reference to this picture, right, how an application transport network, how the data is put into different headers and stuff like that. I just want to show you quickly an IPv4 and an IPv6 packet. And these packets are already there uploaded in Moodle. You can download them once you install Wireshark, and then you can open them, right? Okay, let me figure out where I have that. So just give me a minute. I'm going to share my screen. Can you see my Wireshark screen now? Is it clear, or do I have to zoom? Is it okay? Perfect. So this is the Wireshark tool. Like if you go to help, you see this is about Wireshark, and it's a network protocol analyzer, and I have the version 3.2.3. You search Wireshark in Google, and you should be able to install it either for Linux or Mac or whatever. And once you install it, you can open the packets file, go to open, and then choose the file that you want to open. So these files, v4 HTTP and v6 HTTP, are HTTP packets, one for IP version 4 and IP version 6. I have uploaded it in Moodle, and you can just click on this and then say open, and then you're going to open this file. And once you open this file, you can see the first column. You can see the first thing is the number, time, source, destination. These are the different columns you see. So the number tells you the packet. So this is packet number 1, this is packet number 2, this is packet number 3, and so on. And then the time is in relative time. What is the time difference between this packet and this packet, and the second and third? It's not sequential, right? So it's in relative time between the packets, right? It's not so interesting at this point of time, but let's when I click on one, that's packet. I'm currently clicking on packet number 1. In the column here, you see the packet itself. It says that it's an HTTP. You see the protocol is HTTP. It's an application layer protocol. When we see this picture, so HTTP is an application layer protocol. HTTP runs on top of TCP, and TCP runs on IP, and IP on Ethernet. So that's what we want to see. So you can see HTTP. This is the HTTP header. It runs on TCP. So this is the TCP header, and TCP runs on IP. Expand that, and then IP is put inside Ethernet. And this Ethernet packet is put on the raw wire. So when the packet leaves the machine, right, it's all going as bits and bytes. You can see those bits and bytes, what's exactly going out as hexadecimal down. This is the raw packet that you see down. What Wireshark is doing is it's reverse engineering these bits and bytes, and then it's kind of telling you, okay, the packet that you're seeing is actually an HTTP packet at the application layer, which uses TCP. In TCP, the interesting fields are the port numbers. It's using the source port number as 25162 and the destination port number as 80 and so on. And then the TCP has other header information, like it has the sequence number, acknowledgement. I told you that TCP is a very secure protocol. So you're going to get acknowledgements from the remote side. So all these you're seeing it here. And then TCP has some window size. When we talk about TCP, we will go deeper into this, right? But at this lecture, you just need to know that there is an HTTP header, and this HTTP packet is put inside a TCP header, and the TCP header is put inside an IP header. And you can see we are using an IP version 4. So the IP address looks like this. That's pretty readable, right? So 192.168, blah, blah. The destination is 74. This is the destination IP. So if I click here, and that shows you exactly what the IP header is, right? It has the source IP address, destination IP address, time to live, and all those stuff, right? And this IP packet is put inside an Ethernet header. So the Ethernet header usually has the MAC addresses. So what you see is the source MAC address is represented here, and the destination MAC address. And then the packet is sent out. So someone is saying it's confusing. So you just need to, we are looking at this, right? So if you are browsing internet, so what essentially happens is you're having some user data, and that user data will be put inside an application header. This case, because we are browsing, we are using HTTP. So your user data is put inside an HTTP header, and that whole stuff, this application header and user data, what we call as application data, is encapsulated inside a TCP header by the transport layer. And this whole stuff, this TCP header and application data, is put together, is encapsulated by an IP header at the network layer. The network layer is going to add things like your source IP address, destination IP address, and so on. And then this entire stuff of application data, TCP, and IP is going to be encapsulated by an Ethernet header. And this whole stuff, including the Ethernet header, is going to be sent out of your PC to your next router, right? So this encapsulation is exactly what you see here. So what we are looking at here is the first packet. Packet number 1 is an HTTP packet. So this is the HTTP header, and the HTTP is put inside TCP. The TCP is put inside IP, and the IP is put inside Ethernet. And this is the whole frame. Look at as and when I click the individual headers, I just want you to look at what happens below this field, right? This, when I click here, this is the whole packet, all the 10,600 bits, right? So this is what exactly goes on the wire. And if I click here, this is the whole content, HTTP content, right? So you can see here, this packet is quite big, right? I'm browsing something, and this has the actual content, right? HTTP. But look at TCP. TCP itself is only, quite small, right? This is just the header. And look at IP. When I click here, it's pointing to a different, right? It's just showing it in hexadecimal format, just the header. And this, when I click on the Ethernet, it shows just the Ethernet header. So every header has its own size and so on. We'll talk about that when we deal with each layers. But just play around with this tool. Try to understand that what exactly is an IP packet. Okay. Is there any question that you want to discuss in microphone? Before I show you an IPv6 packet. Just play around with this tool. Yeah, just open this. Let me show you an IPv6 packet. Open v6. It's again an HTTP. Let's take this packet, HTTP packet, right? The lower layers are the same. HTTP is put inside TCP, but now TCP is put inside IPv6. So if I look at the IPv6 header, it looks different from an IPv4 header. We'll look at the details later, right? So the source IP address is an IPv6 address. The destination IP is a destination IPv6 address, right? And this IPv6 packet is put inside an Ethernet header, and the whole stuff is sent out in the wire. So in this case, the packet size is 2,512 bits. So you're seeing all the bits and bytes of the packet, what's coming in and what's going out, right? So this is just an example packet. I did not capture this packet on my computer, but this is a packet that's someone captured, and we are just analyzing it. But you can also capture packets live as and when we do this conversation. For example, you can go here to capture, and then you need to go to the options, make sure that you have all the interfaces there, and then go to capture and then start, right? It's opening me, just hold on a bit. Okay. Capture, start. So I didn't select any interface, that's what it's complaining me. So you have to go to options, enable promiscuous mode, manage interfaces, local interfaces. Just hold on, I just need to refresh my interfaces once. So here are the, okay, let me fix some stuff on my machine. I have a firewall that's blocking the capture. I will show you how to capture a live packet in the next class. But in today's class, I don't want to introduce you too much into that. So what you can do is you just install for now the Wireshark tool, and I have given you 2 files in Moodle, and and you can just go File, Open, and then open this HTTP packet, and then you should be able to see these packets. So are we going to do in detail bits and bytes, and I mean how we divide data in packets? No, actually, I will when we talk about IP header and so on, I will talk about how an IP header looks like. How an IP header looks like. For example, an IPv4 header has an header length. It's always 20 bytes. It has some fields called differentiated services field that deals with quality of service, and things like time to live tells you um, that there are no routing loops and so on. I will tell you what this means, the source and destination IP or the IP addresses, right? So we will deal with all these stuff when we talk about IPv4 and IPv6. And in the examination, right, I can give you one of the question by maybe I'll give you a screenshot in your question paper. You will see something like this, right? And then you will have, you'll just see a screenshot like this. And then I'll ask you stuff like, what is the time to live? What is the significance of time to live? You know, things like that. So it's very important that you understand this tool, right? You understand what it means. You're opening and playing around this tool. It's all okay, but you should be able to tell what is the meaning of this? What does the source IP mean? For example, when you are dealing with TCP, when we discuss, we will deal a lot deeper about this protocol TCP. You need to know what a source port is and what a destination port is, what a sequence number is, what an acknowledgement is, right? When we deal with congestions, like when we deal with TCP, we'll go into details, but um, you know, we will go into this depth, right? I don't want you to remember all these numbers, right? But there is, as and when we go over, you need to understand it from a conceptual point of view, what's going on, right? So for that, in today's lecture, I just want you to understand that, you know, whenever you are doing a web browsing, you are actually creating some user data. You're putting it into an HTTP header. You're adding an HTTP header or the application header, and then the TCP add its own header, and the IP is adding its own header, and then the Ethernet is adding its own header, and you're sending the packet out. And that's exactly what you're seeing here. Here you're seeing, for example, a HTTP packet, right? This is the HTTP data. You're adding a TCP header to it. You're adding an IP header to it. You're adding an Ethernet header to it, and then you're sending the raw packet on the wire. So as and when we go detailed, you know, when we go a little bit deeper into the protocols and when we discuss, then you will understand, you'll try to understand this header a little bit. You'll know what a TTL is, what a time to live is, and so on. But today's class, you don't have to do that. Is that okay? Perfect. Good. So we saw in today's class a sample packet, right? V4 and V6 packet. And I want you to focus also on subnetting. You also need to know um, what a subnetting is. And, you know, I gave you an example of why we already discussed this concept here, why you need to subnet, right? When you're given a block, then you need to divide it into smaller sub blocks, right? And then depending on your network design, you should be able to do that. So in that context, I want to show you an online subnet calculator, right? So I've shared this in the, not this link, and subnet calculator, right? You'll see it in the slide. So it works like this, right? So you can give your IP address here, 8.8.8.0/24. This is the bigger block, right? So when you give this 8.8.8.0/24, this is the block that you got from RIPE. And then you get already some details. This is your subnet address. The first thing is what you have. Let me present it in a different form to you so that you understand it. So we have something called as the um, net network address slash subnet address. So this represents the whole block, this 8.8.8.0/24 that represents a network, right? In the networking term, they call it as network address or the subnet address, okay? And then the /24, right? It's called as the subnet mask. The subnet mask is /24. You can represent it as like this, or you can represent it as 255.255.255.0. There are two ways of representing the subnet mask, right? The subnet mask really tells you how many IP addresses you really have, right? So then you have the range of address. So if you have a subnet mask of /24, right, the range of IP addresses that you are going to have is 8.8.8.0 all the way to 8.8.8.255. So this is the range of IP addresses that you can use. Okay, this is a range of IP address. So how many IP addresses you have? You actually have 256. Okay, so the total IPs that you have in this range is actually 256, but you cannot use all the IPs. Okay, this IP 8.8.8.0 is a special IP. That's the first IP. This is called as the um, subnet IP. You cannot use it. It represents the whole subnet. And the last IP 8.8.8.255 is it's called as the broadcast. It represents in broadcast IP. You cannot use that as well. So anything in between you can use, like 8.8.8.1, it's usable. 8.8.8.2 is usable, and so on and so forth, right? Um, uh, you can do all these. You can use all these IPs, right? 8.8.8.2, blah blah. 8.8.8.254. You can use all IPs from 8.8.1 all the way to 8.8.8.254 for your for your customers, or for computers, whatever you're doing. So this thing is called as the usable IPs. They call it the IP as a usable IP. Your usable IP is only 254. You might have a total IP as 256, but the usable IP is only 254 because the first IP, the .0, is a subnet IP. You cannot use it. You cannot assign this IP to any customers, right? And then the broadcast IP, you cannot give a broadcast IP to any customer. All the IPs that are in between 8.8.8.1, blah, blah, they are called usable IPs. And so you get 254 usable IPs. Okay, this is a kind of um, the core concept of subnetting. Okay. Um, yeah, how do you do subnetting? I think you learned it in the last semester. I would recommend you to go back to that. Or there are tons of tutorials on internet, like dealing things with, binary, how to convert an IPv4 address into binary format, and and then doing and subnetting and all those things. I think you had done all those stuff in the previous semester. If needed, we can do it one more time during one of the exercise sessions, okay? But at this point, I would recommend you to use this visual subnet calculator and online calculator just to understand what different things means. A subnet address represents the whole address, your bigger block, and the net mask, you can represent it as /24, or you can represent it in this form. And the range of address, right? This is the range of address, but you cannot use all the addresses in this range. Some IPs are reserved. Subnet IP and broadcast IP are reserved. So your usable IPs are slightly little bit less. Okay, so this is the kind of a short summary of subnetting. And coming back, now we saw how to divide this, right? We want to divide it. So you can click on divide, right? When you divide it, what we are essentially doing is this slash 24 is split into slash 25, right? You're splitting now the bigger block slash 24 into smaller slash 25s. So now you can see your subnet has, your net mask has changed, right? You have two networks now, 8.8.8.0/25 and 8.8.128/25. So that's what, let's track it with this here, stuff here, right? We have this 8.8.8.0/24. This has been split up into 2/25s, right? So the slash 24 is the net mask. And what are those subnetworks? So it is 8.8.8.0 and 8.8.8.128. So we have split this network into 8.8.8.0/25. And then we have split this into 8.8.8.128/25, right? So this had how many IPs? 254 usable IPs, right? And now you can see from the calculator, you have 126 IPs in each of these smaller blocks, right? So coming back to this picture, so this block had 254 IPs, and each of these blocks are now having 126 usable IPs, right? So if I give you an example IP, for example, I'm giving an IP 8.8.8.25, right? So this IP, right, is a /32, a single IP. It's not a group of IP, which I can represent it as in /32. This belongs to this group, right? Because it's .25. And why do I say this belongs to here? Because this has a range, right? If you look at this range, it starts from 8.8.8.0 to 127 belongs to this range. Any IP in this range belongs to this subnet, right? So the 8.8.8.25 will belong to this subnet, whereas an IP 8.8.8. Let's say 212, right, /32 will belong to this range, right? So I can give a customer, if I assign this range to a customer in Duisburg, and if I assign this range to a customer in Cumberland Fort, right? Cumberland Fort, complex name. So you can see just by looking at the IP, you can tell to which subnet block it belongs to, right? So 8.8.8.212 is something that someone in Duisburg might have, because according to my design, I have split this /24 into 2/25s, and this range, I'm going to give all the customers in Camp Linford are going to get IPs in this range, So I have 126 IPs that I can assign to customers. That means the restriction is I can have only 126 customers in Camp Linford, right? And I can have only 126 customers in Duisburg. So these are some of the constraints, right? And if you have more customers, like if you have 1,000 customers, then probably you need to get a bigger block, right? Your /24 is no longer enough, right? You need a bigger block. You need to get a bigger block from RIPE and so on. So this is the fundamental concept that we are talking about here. You can divide your subnets, right? If you want to go back to the previous master block, just click on this /24. It's going to show you the range of address, usable IPs, and the number of hosts you have, and the net mask and the subnet address, and then divide your /24 to 2/25s, and then you can keep on dividing the 1/25 into its component /26, right? So like that, you can keep on dividing, make into smaller subnets. Then you will end up something like a tree structure, right? That's exactly what you want to understand, because once you go into IP routing, the routing table is also going to be organized as a tree where you will have the bigger blocks, your aggregate um, blocks on the top, like your um, 8.8.8.0/24, and then you'll split it into /25s, right? And /25, you can split it into 2/26, and so on and so forth. You keep on dividing stuff until you reach the final node, which is the /32. You cannot divide a /32 more because that's just only one IP address, right? /32 is just a one IP address. That's what a customer will get, a dynamic customer, right? We saw in the picture 8.8.8.5/32. This is a single IP address. A single IP address will have a net mask of 32. You cannot divide it anymore. And that's why you're going to give it to your customers, right? And this specific IP address is called as the, in IP, what we call as the more specific IP, or the more specific prefix. You have to get used to these terms like IP. Sometimes people will use the term prefix, and so you can use it interchangeably, right? This 8.8.8.5/32 is a single IP or a prefix, okay? And that's how you divide your subnets, and then you need to at any given point you need to know the structure, and this concept will be useful very much when we discuss about hierarchical routing. So this takes us to an interesting discussion about hierarchical routing. So why is it so interesting? Why are IP addresses done like this? Let's take an example of our postal system, right? What happens in a postal system is, end users, they have their own address, right? They have their house and they have their own address. And then there are some post offices in between, right? So let's call it as a regional post office, right, in your city. And let's say there is one national post office in a country, right? So let's say a person is there in one country, he's sending a letter to another person in another country, right? So let's say he's X and he's Y, and this is his home. And each country has their own national post office, and then regional post office. And this is the address of the user, right? So let's say the user has some street number. I'm just going to say street X, and let's say he's there in a town called Camp Lindfort, and he's in Germany. Okay, and the name of the person is X. Okay, and this person is Mr. Y. He's living in some street address Y. He's living in a city called Madrid in Spain, and Spain is the country. Okay, let's say he's sending a letter. Okay, you know what happens? Somebody picks up the post and he sends it to the regional post office. The regional post office guys, right? Let's say this guy is sending a letter. Y is sending a letter to X. So what he will do, he will in his address, right? He will write this address, right? So the address will be X, and then street X, the destination address, and then come Linford, and then Germany. This will be the kind of the content of the address, right? The destination address. Let's look at this address. It has a hierarchy built into it, right? The regional post office, right? Once they receive the post office, they probably look at the city, right? And then on the country where it needs to go. As long as they know this is Germany, they don't have to do anything. They just have to send it to a national post office. The national post office has they look at only at Germany, the aggregate address, right? They don't care really at the national post office level. They don't really care about who is the recipient. They don't even know the street address and so on. All they are interested in are probably which city and country, more importantly, the country. Because from the national post office, you can send the letter to Germany, to other countries as well, right? So once the letter comes through, through a flight to the national post office, at the receiving country, the national post office, they look at the city, right? They know that this letter has in Germany, it's already landed in Germany. So they only look at the city here. And then the regional post office, who's responsible for delivering the letter to the user, probably they are only looking at the street address, right? They're just going to look at the street address and then they are going to put it in the post box. And who is going to care about the name of the person? Only someone inside the home, right? You are living in a family. Then the letter has to be, it's either to you or to your father or to someone, to your partner, whoever, right? So someone inside the house is going to look at this, right? So there is a hierarchy built here, right? So the address, this Germany, this is an aggregate address in terms of IP address. Compare this to this 8.8.8.0/24. This is this aggregate, this big thing. So this is how the networks are also designed, right? So you are a network, right? So you are a small network. So you are kind of an regional post office, right? So your ISP is kind of regional post office, and your transit, right, is kind of a national post office. And transits are going to talk to other transits in other countries, right? They are kind of national post office. So let's take this as an example, right? So I'll write the equivalent IP terms here. So this is going to be your kind of a domestic ISP, right? And the national post office is kind of a transit uh, ISP, right? So this is transit and this is domestic. So the transit guys are only interested, they only want to know about the bigger pool of IP address, right? So they don't really care whether it's, that particular user has got 8.8.8.5 or 8.8.6. They don't really care. All their routing is based on their big aggregate address. And as you go more towards the end users, like a domestic ISP really needs to know about the more specific subnets, right? So the more specific subnets are um, the 8.8.8.0/25, the 8.8.8.0/26 could represent your street, and then that person 8.8.8.5/32 could actually represent one user, right? So all these addresses are interesting only for the domestic ISP and to the routers that he is building, right? Your DSL router, more closer you're coming to the user. So this is the relationship, how the hierarchy corresponds to routing in the broader sense, right? So whenever you are working as a transit provider, let's say you are running this network, transit network, you might be having a lot of routers in your network. If you check the routing tables, you'll only see the aggregate routes. You will not see any of these more specific routes inside a transit network. So the domestic ISP, he is going to announce through BGP only the aggregate prefix. He is not going to announce more specific prefixes here for many reasons, because the more prefixes you announce and the size of the internet routing table is going to grow too much, and then your router is going to crash and all those things. So you also have to protect your routers from getting these more specific prefix. Let's say you're a transit provider, and let's say your domestic ISP is sending you a lot of /32s. If he's going to send you like 10,000 /32 IPs, and if you're going to put all these IPs in your routing table, then your router is probably going to run out of memory and crash and things like that. So this kind of hierarchy you need to understand. this. And the most fundamental thing to understand this hierarchy is you should be able to do this subnetting. Okay, so there was a question, could we substitute the transit ISPs with global ISPs? Yes. I mean, just forget about this transit ISP and global ISPs. You just need to know that, they are just interconnecting several domestic ISPs with each other. And in essence, it's just a name and some kind of business relationship. But from a technical packet transfer and connectivity perspective, it doesn't make much of a difference. Okay, but you understand this concept of hierarchy, right? How the postal, what an address means, which subnet is interesting at what level, and so on. That should be very clear to you at this stage. What we call as the hierarchical routing. This is what we called as the hierarchical um, routing. Internet is organized as an hierarchy, and that hierarchy starts with your subnet. And the routing happens in a hierarchical fashion, as I showed you. We'll talk about this later, but at this stage, you should be comfortable understanding, you should be able to understand this visual subnet calculator, and then give any address, right? Whatever address that you think you can change the subnet masks, and then you should be able to find out how many hosts are there in each subnet, and so on. If you understand this, then it's good enough at this stage. Okay, so I think we have covered quite a lot of concepts today, and this two charts kind of gives you an idea of how many IP addresses are there. A /32 subnet mask has only one IP address. A /24 has 256. There's a total number of IP address, but there is two IP addresses you cannot use. The usable IP address is -2, right? So this chart can tell you the IPv4 and the equivalent subnet mask. And then this is an IPv6 chart. I would suggest just wait a little bit till there's a separate section on IPv6, and then you will understand this. Right now, it may be difficult for you. Maybe you have not done anything with IPv6 so far. So for this class, just try to understand this chart and try to do some subnetting. Go to the website, take some subnets, split it up into smaller groups, and try to understand that. Okay. So I think our first class ends here. I just want to get some feedback from you on some aspects. Is the connectivity good? Like, are you able to hear me clearly? Is my voice and the video that I am showing you, is that clear? Are you guys able to follow this stuff? Cool. And perfect. And regarding the content, Uh, is it um, is it okay? The space, is it okay for you? Uh, like um, like the speed, and I don't want to put too much of information in you. And yeah, so from that perspective, is this space good? Okay, space is also good. So I will put the drawings that I am scribbling here. It's a little bit difficult to draw too many things, but I'm going to put this as a PDF file into the Moodle as well. Regarding the recording, what I am do is I'm not going to record the whole session because each recording will be like 4 hours. Then I have to edit this pause and the breaks that we have in between and so on and so on. So what I intend to do is I'm going to record it myself as a kind of a summary going over the slides, and then make a shorter video, because I know if I put a 4-hour video, you're also not going to listen to them. I'm just going to put the main points, the things that are really important, as a kind of a summary video recorded, and then I'm going to put it in the Moodle. As I said, just come to my class, try to make sure you see I'm drawing some things on the board, which you will not find in the slides. And that makes sense only if you come to the class. So I do understand some people, maybe you are not able to join the class on a Saturday. But unfortunately, because of this COVID situation, um, the timetable is cramped and we need to cover somehow the 60 hours of lecture. So that's the whole idea. So as far as lecture exercises for this, just have a look on the exercises. I don't think you might be able to answer any of the exercises questions for this class. And we will continue tomorrow. We have another session tomorrow. And maybe after tomorrow's session, let's see how much we are progressing forward. And let's do exercises maybe for the weekend. Okay.